This new chapter is all about polynomials, and in the first lesson we're going to learn about modeling polynomials. Poly in math just means one or more, so it could be 1, 2, 3, 4, any number. Polynomial is a sum, or one or more terms, so we're adding them, a sum. Now in practice that means you can also subtract them. Addition and subtraction are essentially the same thing. Each term in the polynomial is a product, so multiplying, of a few things. A numerical coefficient, so basically just a number out front, we call that the coefficient, and any number of variables. The variables can have only positive integer exponents, and they don't have to have an exponent at all. So they cannot have a negative exponent, they cannot have a fractional exponent. And you haven't seen fractional exponents yet, but an exponent of half would correspond to taking the square root of a variable. You can't have anything like that. So let's, one last thing. Sometimes polynomials are referred to by the number of terms, but that really only applies if there's 1, 2, or 3 terms. A one-term polynomial is a monomial. A two-term polynomial is a binomial. A three-term polynomial is a trinomial. And we don't bother after that. It's just a 4-term or a 5-term polynomial, or however many terms there are. So here's a term with a few arrows pointing at it. So 3x squared y. So again, keep in mind that this is a product. We're multiplying all of these things. And that's why, because we're now using variables, it's important not to use the x as a symbol for multiplication. When you see the 3 beside the x squared, beside the y, keep in mind that all of these things are essentially being multiplied. And each of these we can talk a little bit about. The 3 is our numerical coefficient, or just coefficient. If there is no number, then essentially the coefficient is 1. So we can always find a coefficient. The x squared, that has an exponent, and keep in mind it's positive, and an integer. The y doesn't have an exponent, but that really just means that it has an exponent of 1. So, 1 is a number that we often don't write in the case of an exponent or in the case of a coefficient, but there really is an exponent of 1 there. And this is going to become important when we talk about order. So you need to pay attention to the fact that if there's no exponent, it really means there's an exponent of 1. And obviously here we have the 2 variables. Now, because one of the properties of multiplication is that you can multiply things in any order you like, we could rearrange the 3, the x squared, and the y. So for instance, we could write this as x squared y 3. That's the same sort of 3 components all being multiplied by one another. We could write it as y x squared 3. We could write it as x squared 3y, y 3x squared, and 3yx squared. In fact, with these 3 components, the number 3, x squared, and y, there's 6 different ways we could sort of put them all together. We don't really want this sort of confusion, so there's a little bit of grammar, if you like, or style in the way you write these polynomials. Typically, you want to write the terms with the numerical coefficient first, so the 3 in front. And then if you have more than one variable, you want to put the variables in alphabetical order. So x and y, if you had a and b, put them in order. And that way, if everybody follows the same rules, then 2 polynomials or 2 terms that are the same look the same. They don't have sort of different ways of being written. So 3x squared y would be the preferred way to write this particular term. Again, though, that's just sort of a grammar thing or a style thing. If you did sort of combine x squared y and you multiplied that by 3 and you had x squared y 3, you could just rearrange the terms, but you need to recognize that it is the same thing. Now, I mentioned a second ago, we need to talk about something called the order. So the order of a term is the sum of the exponents. So again, sum, adding, so sum of the exponents. So, for instance, the one above, 3x squared y, the x has an exponent of 2, the y has an exponent of 1. We're not ever worried about the exponents on the coefficient. This is just the exponents on the variables. So we have two exponents, a 2 and a 1. We add those together and we get 3. So 3x squared y has an order of 3. So let's take a look at a few examples of terms that have an order of 1. So 2x, for instance. The x has no exponent, therefore an exponent of 1, and there's only one of them. 3y, z. So essentially, if it's order of 1, you're only going to have one variable, and it's not going to have an exponent that you would write, so therefore just an exponent of 1. The numerical coefficient has nothing whatsoever to do with the order. Let's take a look at a few with an order of 2. So one way we could get an order of 2 is by having two variables, each with an exponent of 1, so 5xy. We could have something like 6x squared, where the single variable x has an exponent of 2. Again, the coefficient really doesn't make any difference here. 23xz, for instance, is fine. How about order 3? Here's where it starts to get a little more interesting. We could have a single exponent like 7x cubed. We could have a couple of, single variable like 7x cubed. We could have a couple of variables, so let's say 5xy squared. So here the x, again, has an exponent of 1. The y has an exponent of 2. You add those together, you get 3. So that term has an order of 3. We could also have three variables. So for instance, 2x, y, z. There's no exponents written there, so each one has an exponent of 1. And you add them all up, 1 plus 1 plus 1, you get an order of 3. Throughout my notes, I'm primarily going to use x, y, and z for my variables. In the text and in other places, you're going to see just about every letter under the sun. A, B, C, S, T, U, all sorts of letters. If you are doing a word problem that's maybe science-based, sometimes it makes sense to have a variable other than x, y, z to represent something like distance or length or speed or time. But if we don't have any context, it just is a much easier convention to use x, y, z. There isn't really anything special about x, y, z, but it just becomes the sort of commonplace variables that we use. Now, that's the order of a term. The order of a polynomial is the same as the term with the highest order. In other words, a polynomial is a sum of terms. So let's take a look at a polynomial. So we could have a couple of terms like x squared plus y. And the first term there, x squared, has an order of 2. The second term, y, has an order of 1. So the whole polynomial has an order of whatever the highest of those is. So since the highest is 2, the polynomial has order 2. Let's take a look at a little more complex example. What if we have 3xy plus 5x cubed minus 2xyz? So the first term there has the two variables, neither with a written exponent, so each has an exponent of 1. Add them together, you get an order of 2. So that exponent has an order of, or that term has an order of 2. The second one is pretty easy. That has an order of 3. The third one, each of those variables, x, y, and z, has an exponent that's not written, which is 1. Add them together, you get 3. So that also has an order of 3. And therefore, the polynomial has an order of 3. Now, if you only have terms with a single variable, like every term has only the variable x, then again, a little bit of math grammar or math style is to put the terms in declining order. So for instance, let's say we had 5x cubed plus 8x squared minus 11x minus 3. So that first one, I'm just going to write order once. The first one has an order of 3. The second one has an order of 2. The third one has an order of 1. What do we do with this minus 3? Well, One way to think about it is if we had the variable x, the only way to sort of make it disappear is if it has an exponent of 0. I started this lesson off by saying the exponents have to be positive. Whatever way you want to sort of explain it, we can refer to a number on its own as having an order of 0. And so this polynomial has 4 separate terms, and we've got them in declining order. But this, again, is just grammar. It's just a little bit of math style. You may well see this same polynomial written in a different order, and it's the same thing. So, for instance, we could have the 8x squared first, followed by the minus 3, followed by the plus 5x cubed, followed by the minus 11x. Doesn't matter the order in terms of what it represents or its meaning. But again, it's nice to be able to simply look at it and be able to determine whether one polynomial is the same as another. And so if you follow these sort of steps of best practices or grammar or style, then everybody who's writing the same polynomial is going to write it in the same way, and we won't have any confusion. Now, this whole lesson so far has just been preamble, because what we're really supposed to be talking about is modeling polynomials. Now, we can model polynomials with something called tiles. They're often referred to as algebra tiles. And there's a few different conventions that are followed. However, they're somewhat inconsistent. So I'll try to do it in the same way the textbook does it. So with these algebra tiles, typically at first you have 3 shapes of tile. So you have a big square, you have a rectangle, and you have a small square. So the big square is meant to represent x squared, and you can think of it as having dimensions of x by x. The rectangle has exactly the same length as the x squared tile, so it also has a length of x, but it's a much narrower width, which we assign a value of 1 to. So that tile is just an x tile. And the 1, the small square, or the small square represents 1, and it has the same width as the rectangle, but not the same length. Now, because x is meant to represent a variable quantity, x could really be anything from 1 to 10 to 100 or 1,000. So you don't want to get hung up on how many of these little 1 tiles you can fit in. If you're dealing with physical algebra tiles made of plastic or wood or whatever, they never quite match up perfectly. However, they're always about 4 or 5, but you don't want to get hung up on that, because really it's meant to represent a variable quantity. So you can use these algebra tiles to represent various polynomials. So let's say, for instance, you wanted to represent 2x squared plus 3x plus 4. So 2x squared means you have 2 of those big squares. So there's 1x squared. There's another x squared. 3x's means you've got 3 of those rectangles. So there's 3 x's. And 4 1's means you've got 4 1's. So 1, 2, 3, 4. Now, how do you represent negatives? Well, I'm not going to bother coloring these in, but if you look in your textbook, you'll see that the colors can be used to represent positive and negative. In your textbook, the convention they use is yellow for positive and red for negative. So I'm just going to make that note there. Yellow for positive and red for negative. But there's lots of conventions, and it's actually pretty tedious, as I said, to draw these out. So when we're going to play with these, I'll suggest you use a website, and I'll give you a few to choose from, and I'll send you the links for these. So here's one, and I'll give you the website for it. It's technology.cpm.org. So this allows you to represent them, and you just click on them to change them from positive to negative. So they represent the x and the x squared as kind of a light blue when they're positive and a red when they're negative. And you just click on them to change them to negative. The 1 they represent in a dark blue color. These are a little more sophisticated because we also have a y and a y squared. Not every implementation of Algebra Tiles does that. And if we want to sort of give them a little bit of difference, we can change the size on them. We can also have a product of x and y. And if you notice, the x squared tile is meant to be the same height there as the xy tile, and the y squared tile is meant to be the same width as the xy tile. So it's kind of consistent in that regard. And again, you can click on the y or the y squared. Looks like everything goes red when you make it negative in this particular implementation. This doesn't allow you really to do a whole lot. This allows you basically just to kind of play around and represent them. There are other sites where they actually walk you through various exercises. So this one is mivu.org, and this actually walks you through some exercises, and there's a whole bunch of different activities you can do, from modeling expressions to simplifying them to adding them to solving equations. Here they're just getting you to model them. So 4x minus 4. So they've got different colors for the positive and all red for the negative. So they've got an x squared tile and a blue, an x tile and a green, and a yellow for the positive 1 tile. So 4x minus 4, we would drag out 4 x's, and then we would drag out 4 1s. And now what we've got there is 4x plus 4, so we need to change all the 1s to negative. Oh, this is not allowing us to do that, so we're going to have to either get rid of them somehow. There we go. We can drag them to the trash can. And instead of dragging out positive 1s, I'll drag out negative 1s. And I've got 1, 2, 3, 4. And presumably, there we go. We get a little bit of feedback at the bottom. Correct. Click new to try another problem. So you can go through all sorts of problems that way. And then one final one is this one right here, which is actually on the National Council of Teachers of Mathematics site, nctm.org. And it's the same sort of idea, maybe not quite as many different types of activities. They go straight into the solving equations mode. And this one, so you can click them. Oh no, you select it, and over here you make it go negative. So they all have slightly different ways of doing that. Now, if you're already familiar with polynomials, or if you're picking it up pretty quickly, you may think that this is kind of pointless. And certainly at first it does seem to be kind of a waste of time and kind of tedious. But you would be surprised later on when we get into more complicated matters, especially when we get into factoring. There's some very interesting insights that can be drawn from being able to model these polynomials in diagrams. When I learned algebra, these sort of things didn't really exist, and I just learned it purely abstract way. And so as a teacher, I learned about algebra tiles, and I really was quite intrigued by some of the insights that you could glean from representing these polynomials in diagram form. So don't give up on it if you think it's too easy, and if you don't quite understand how the algebra tiles work yet, don't worry, we're going to get lots of practice with that.